सर रेकॉर्डिंग ऑटोमॅटिक स्टार्ट केलंय.
हो, तर ते क्लाउडवर होईल ना रेकॉर्डिंग?
क्लाउडवर आहे.
हा, कारण आधीचं माझं माझ्या लॅपटॉपवर झालं
हो
आहे.
हो. मी
तर ते
काढले सगळे त्याच्यातले, आता ते झाले रिकामं क्लाउड स्पेस.
हो, मी आता
आता
नंतर
बरेच.
तुम्हाला विचारेल कसं ट्रान्सफर करायचं ते.
हो चालेल चालेल चालेल.
नंतर आता लेक्चर करतो, नंतर
हो
सांग.
हो, तुम्हाला होस्ट केले आता.
हो, थँक्यू मॅडम,
ओके
थँक्यू.
ओके.
Mr. Narayan, we will wait for another 10 minutes and then begin. Okay, Mr. Satyanarayan, can we start now? Hello. Are you there, Mr. Narayan? Should we begin, Mr. Ambadkar?
Yes, sir.
Okay, now you and Suryanarayana too are appearing on my screen, but Satyanarayana is not responding. I don't think he's there. So at least you respond because I can't start unless at least one participant should be there, isn't it?
Yes, sir.
Without that, I don't know whether my screen is visible to you or if there are any other difficulties. No, if there is no response from outside, I don't know. Anyway, so we'll be covering the topic of cogeneration in this lecture. This topic is bit difficult in the sense that it contains almost the same syllabus what you have learned in boiler, turbine, no, it's combined. So it's a pretty big chapter, about 20-21 pages. And many times the paper 4 gets a one big problem, 20 marks or 10 marks on this topic invariably. So we have to concentrate on the concepts and then practice on the problem solving because many times the problems are based on cogeneration as they are based on boiler and turbine. So in this chapter, what we will be looking at basically is the cogeneration definition, need for cogeneration, why we want to go for cogeneration, its application in real practice, what are the advantages, classification, what are the saving potential, heat balances, steam turbine efficiency, trigeneration, and micro turbine. All these are necessary for clearing our concepts regarding the energy efficiency, particularly in the heat energy. So let us start. What is the need for cogeneration? First, understand what is cogeneration. Cogeneration means it is not your main product. Main product is something else. And along with that, a ancillary generation is being done. For example, a sugar factory is there. What is the main purpose of sugar factory? Is to manufacture sugar. Now, in this process, they generate a lot of raw materials like the bagasse, the Sugar cane is squeezed, juice is taken out. What remains is the residue called bagasse. Now, this bagasse is a waste product for sugar factories. But if you dry it, it becomes very good raw material for burning in boiler. So if we use this bagasse, which is freely available, at most free of cost to the sugar factory, and burn this into a small WBC, FBC, fluidized bed combustion boiler. There, your fuel input cost is zero. So whatever you generate is almost zero raw material cost, only the process cost, establishment cost, that is the cost, capital cost, and the O&M charges. You can generate 3 megawatt, 4 megawatt, 5 megawatts, depending on what is the volume of raw material available with you. So this generation, which is a secondary generation, I will say, is called cogeneration. That is what the factory is co-generating sugar and electricity. Right. Take a second example. You are visiting a industry. Now the industry is manufacturing cloth mill. So their basic need is heat energy. They need heat for boiling water. They need heat for drying the clothes. They want heat for some other heat sinks and process requirements. So steam for heating is used at multiple levels. Some steam at 120 degrees centigrade with 2 kg pressure. Somewhere the heating need is very light, that is at below 1 kg pressure. Somewhere the requirement is only hot water for the process. So their main purpose of using the fuel is to generate heat. Now, in this process, we found that heat they want, suppose at a low pressure of 10 kgs, 10 kg and the temperature of say 200 something. But then I will say that you are anyway generating, I mean burning fuel and generating steam. So part of the steam can we divert for making a electricity generation. Use a small reciprocating engine or say the rotary turbine, generate power, and after condensing the steam at desired pressure from the turbine, the same steam can be used for process. If you do this, again it's a cogeneration. Your main generation product is heat and you have also generated electricity. So sometimes fresh steam is used for electricity generation, and after that generation when it is condensed, it goes for the as a heat source for the processed heat requirements. So that is also a cogeneration, right? So you know what is cogeneration, simultaneous generation. Now, here a balance of typical coal-fired power plant they say. You have already seen the coal-fired power plants in chapter 2. So I will not repeat. You can go through this diagram. The diagram is very simple. See, the output, input, the requirement at different stages. Suppose this is the input. What is the energy input? Coal multiplied by the gross calorific value. The total value of heat is 100 GJ. GJ is actually gigajoules. It's an old system of measuring heat. Nowadays we don't use it. All your units will be in kilocalories, right? The relation between kilocalories, 1 kilocalorie is equal to 4184 joules. That you have to note down somewhere. If at all there is a small question on MCQ, convert 2 kilocalories into joules or gigajoules like that. So you should remember that. Okay, then all the losses are indicated. Loss going through the hot surface, energy loss from blowdown, and so on and so on. And a heat balance is created here. This is just a illustration. When we will solve the actual problem, then you will realize what are the use of different parameters. Now here, there is one simple explanation. Principle of cogeneration. That means what? Now let us look at this particular figure
Hmm.
showing the advantage of cogeneration. Now suppose, first example, suppose I want electricity to be generated 24 megawatt and also my heat requirement is of certain kilocalories. Now to generate 24 megawatt heat, I mean electricity, with 40% efficiency, which is also higher side, it never exceeds 35, 38%. But okay, to generate for 24 units, I will need a heat unit of 60 because I am generating it at 40% efficiency. That means 60% losses are involved. And therefore, out of 60 units which I received by burning the fuel, only 24 units are converted into heat. Then when I want heat, say 34 units, I will have to burn a fuel of 40 units only because this burning process directly fuel to heat is 85% efficient. So a factory needing these two parameters, they want electricity also 24, heat also 34. So they have got a separate two streams. This is one for electricity, this is one for heat. As a energy auditor, what I will suggest them, here you are spending 100 units of fuel or 100 units of heat is supplied by the fuel. Out of these 100 units of heat, you are converting 24 to electricity, 34 to heat because their efficiencies are less. So for this requirement, you have to use 100 heat units. If you use cogeneration, what happens? Cogeneration has a tendency to generate at 85 to 60, 85 to 90% efficiency. Cogeneration. Why? Because the loss of steam going to the ambient here as a result of this process is a 42 units. These units are not wasted. All these 42 units are utilized for generating heat here. Therefore, the wastage out of this process is 42, whereas the wastage here is hardly 10 because the heat is not exhausted to the atmosphere. This heat is utilized for useful gain. You get the point. So for the achieving the same parameters, you will use only 68 units of heat generated by the fuel. There will be a drastic saving in fuel. In earlier two separate processes, you will be using 100 units of heat. Here, you will be using only 68. That means you have a saving in fuel. And particularly if the fuels are costly, like say LNG or the petroleum products or even coal, the saving is considerable and therefore cogeneration has an advantage. You are controlling the wastages going into the atmosphere by using cogeneration. Got the cogeneration advantage. Now, on my explanation, you can read through this para. That is what they have written there. What are the technical options for cogeneration? Where you can use cogeneration? As an energy auditor, you must advise the industry or the factory that yes, cogeneration can be used in your process. In what way? What are the different types of using cogeneration? One is steam turbine cogeneration system. Steam generation cogeneration system. That means what? Total heat generated by the fuel is partly used to operate steam turbine and partly used for the process. These are the schematic diagrams. These are the standard symbols for the applications done here. I'll give you a little better. Yeah. So the turbine, which is a steam turbine, is in different types. Look at this turbine. Fuel is burned in a boiler. Water is heated here. Steam is generated. the steam is going to the turbine inlet. Remember, the smaller end of the turbine is high pressure end. Larger is the low pressure end. So the steam is entering at high pressure and expanded through number of blade stages. As it expands, it loses heat as well as pressure. It rotates a turbine rotor which is connected to generator and it will generate electricity. Now, when the steam reaches at this point, which is the exhaust point, the pressure and temperature of the steam has come down. So total heat contained in the steam is less. This low heat, low pressure temperature steam is entering into process for say cloth drying or heating the water or some all other functions in a factory as per their requirement. And then after doing the work, the condensate will go through, pumped back to the boiler and the cycle continues. What is the advantage here? If you do not use this steam for the process, what otherwise you will do? You will exhaust it into a condenser. The condenser will cool it down by using cooling water. Going to cooling tower, it will go to heat will go to atmosphere. And that is the loss. And here the power generation will be there. Instead of allowing the heat turbine steam to condense, that means at the lowest pressure, you tap it prior to that. And while it has a pressure and temperature, use it for process. This is one. This type of turbine which does not exhaust into a condenser is called a back pressure turbine because the steam coming out of the turbine has certain pressure. Now take this case of turbine. In this turbine, what they are doing, partly they are tapping the high pressure steam. After doing part work, it will be exhausted here. It will be given to the process and back to boiler. And remaining steam, some part of the steam, will be allowed to exhaust in a condenser and the water will be going to cooling tower and the usual loss is there. The condensate here will again go to the boiler. So it is extraction condensing. That means what? Steam is extracted before it is allowed to finally cool down in a condenser. It is in the process of doing work, but at certain temperature and pressure, we take out part of the steam, use it for the process. Here, the entire steam is taken out. The turbine is not allowed to condense in condenser. It's a pressure itself is entire going to the process. So this is back pressure. This is condensing turbine. When the turbine exhaust goes to condenser, it is called condensing turbine. This is non-condensing or back pressure. Now, this is extraction condensing because part of the steam is extracted. So it is extraction turbine and also a condensing. If there are number of extraction, that steam can be tapped or extracted at this point, as per the requirement of the process. As many pressure and temperature points you can have from the turbine before the steam is allowed to go to condenser. You got the concept clear? So it is a back pressure turbine, extraction condensing turbine. Taking the decision whether we should go for this type of turbine or this type of turbine will be dependent on requirement of that factory. Whether the factory needs only one tapping point for process and the steam is large enough to meet both the requirements. That means heat load as well as electrical load. Then it is a extraction condensing turbine. If the requirement of steam is larger for this purpose, we don't have that much steam. So whatever steam is there, partly we will use for turbine and the same entire steam will be going to the process for doing the heat work. Here there is no condenser, no losses. One way of using it. Here the electric generator part is turbine. In second system, it is the gas turbine. Only difference is that gas turbine cogeneration systems. What is gas turbine? Here, this is a gas turbine unit. The fuel plus air mixture goes here. This is middle portion is a combustion chamber, furnace you can say. Normally, the fuel here is gas. It's a gas turbine. So gas plus oxygen in the air gets mixed under high pressure. The combustion takes place here. The high heat generates very high temperature flue gases, and the gases are exhausted through this turbine. This is a compressor stage, this is a turbine stage. This exhaust of the gas is going through the chimney, right? Here, the flue gas is going through chimney. But the gas going through the chimney has very high temperatures, as high as 500 to 700 degrees centigrade. Now, such a high temperature heat in the form of gas, if we allow it to the atmosphere, environmentally it is not good, one thing. But secondly, you are losing precious heat because this heat you have obtained by burning a very costly fuel, gas here. So what I will do, I will not allow the heat to go to the atmosphere. The gases I will divert to a boiler. This boiler will not use any fuel, but the water coils in this boiler will be heated with the help of the high temperature gases. So this boiler will be utilizing the waste heat in these gases, and that heat is converting water to steam, which otherwise in normal boiler what we do? We put in fuel, burn the fuel, create a furnace, and the fuel generates the heat for converting water into steam. Here the fuel component is saved because you have ready-made high temperature gases. So here the gases will convert water into steam, and the gas temperature will cool down, of course, because they have imparted the heat to the water. And then the cool gases, say at a temperature of about 150 degrees. That means a temperature drop of the gas temperature is from around 500, 600 to 150 to 200. Since 300 degrees heat from such a bulk of gases is pretty high, and we can have a source of steam. This steam will be used for the process in the industry. If not required by the process, we will use it for steam turbine generating power. So this is a cogeneration for using gas turbines.
Sir, here in this, which is the compressor and which is the turbine? First one is a turbine.
The where the air end is there, it's a compressor.
Okay.
Atmospheric air through filters and coolers comes to the compressor. And this fuel, the indication is wrong actually. The fuel is entering here at the combustion chamber, just like your scooter or any IC engine. When it is compressed, it will give fuel. So fuel is here. Air coming to the combustion chamber is high pressure generated by this compressor. So air is sucked in, pressurized, given to the combustion chamber. Fuel, that is gas, is given directly to the combustion chamber. Here is the explosion, or we can say the fire ball. This high temperature fire of course generate the gases of combustion, product of combustion, and these gases will try to force themselves through the turbine blades. They will rotate the turbine. Now the compressor as well as turbine is on the same shaft as generator. Now the next question you should logically ask me, if power is generated by only this cylinder turbine, part of the power is utilized by the compressor for compressing the air because it is on the same shaft. When this rotates, this rotates. But the blade arrangement in compressor is it is sucking the air from outside and pressing it inside. Here, the high pressure result of combustion, that is gases, are at high pressure here and they are expanding on this. So they say nearly 60% of the mechanical power generated by the gas turbine is consumed by the compressor alone. They say 55 to 60%. Remaining mechanical power, torque, is given to the generator and it will produce electricity. So compensate this high pressure and high temperature gases going into the atmosphere. Cogeneration is the best method. Use these gases as a feed-in or the fuel for this boiler. These gases will then use the water converting into steam and then the steam turbine will have an additional generation. So total together, there will be efficiency improvement. Right. Reciprocating engine generating systems. Here, only the prime mover is different. In earlier we have seen steam turbine, then gas turbine. Here, IC engines, see internal combustion engine. Internal combustion engines are very well known to you. Internal combustion engines exhaust at high temperatures. Their gases are very hot. But their shell in which the piston and cylinders are operating like this, they reciprocate. Due to the friction and the compression ratio, the heat is generated inside and the entire thing becomes hot. So unless you take out this heat from the jacket of the engine, it will not remain cool. So you used to have one oil cooling cooler, one air cooling cooler, a water cooling for the jacket, three types of cooler. This oil cooler is for the lubricating oil cooling. Another air which is feed into the IC engine, and this water is taking out the heat from the jacket. Three coolers. The exhaust of IC engine is again 450. Once you get a exhaust of high temperature, whether it is gas turbine, whether it is IC engine, whether it is a high temperature furnace, you get a heat source. And then his heat source can be converted for a fuel for the boiler, which is not using any fuel, but this heat is using the boiler water to convert to steam. And this steam or water, hot water, whatever is the process requirement, it goes to the factory. The factory uses this. If there is no requirement here, the steam can be used for operating a steam turbine and generate power. But normally, these cogeneration schemes are for very small purposes. MSME type of factories where they have one large IC engine but not large enough to produce power on the steam. So the steam, which is a secondary generation or cogeneration, normally used for factory internal process purposes. After cooling down in the process, the heat is taken by the process and the cool down condensate goes back through these coolers and goes to the boilers. Why these coolers? Because this condensate at suppose a temperature of 50 degrees, lower temperature, is getting the heat. They are extracting heat from jacket or the lubricating oil or the air, and that heat is absorbed by this water. Water temperature raises to say 60, 70 degrees. It goes to the boiler, further heated by the exhaust gases and converted into steam. That's the process. Okay. Remember that whether it is a pulverized boiler or a cogeneration boiler or fluidized bed boiler, the boiler exhaust temperature of the gas is restricted by the pollution control board. Why? There is a reason. Because you will say why 200 degrees heat also should be allowed to the atmosphere. Why not extract it further so that we can bring it down to 100 or 80 degrees and then allow it? We are wasting this heat, isn't it? The reason is the flue gas contains different products of combustion. That is NOx is there, SOx is there. There are other multiple macro elements which are oxidized and their oxides are going like uh, O2 is there, part of the O2 you have seen. Sulfur dioxide, magnesium oxide, nitrogen oxide, all these. And we have seen that when these gases go up and their temperature lowers down, they react with the moisture in the air and form acids. Fine. So long as they are forming acid outside my factory, beyond my chimney, I am least bothered. But suppose I reduce the temperature within my factory. If I don't allow the temperature up to say 200, what will happen? The gases will cool down in the process itself and form acids. These acids will corrode the entire steel infrastructure which is here. And that will be a costly thing because then you will have to frequently replace the entire infrastructure, which is very costly, not in the original cost, but also the erection cost, also the downtime of the plant. So that is not viable solution. So what we do, we keep this temperature above 150 because the acids form at a temperature below 150. So ideally, you can have the exhaust gas temperatures 150 degrees centigrade. But we don't take a risk. Suppose I try to keep it 150 and it goes down, occasionally it goes down to 100. Then for that particular period, it will damage my plant. The acid formation will be there. So to be on safer side, we always keep it around 200 or 250. That is the reason why we are allowing this waste heat to go to the atmosphere. Got it? If you have got any questions, you can ask me.
Sir, one question in the just basically this steam after using in the process
Yeah,
that that is getting converted into the water, right? And that water is again feeded to
correct.
oil cooler, air cooler, and water. Okay, then
Huh.
again it absorbs the heat from this oil, air, water,
Yes.
and again it is fed to the boiler. This is correct,
Oh.
sir?
Yeah. Because what we want to recover, energy auditor is a miser, conjuice. He wants to collect heat in whatever small quantity available and use it. He doesn't want to waste it. So what I am doing, when this cooler is there, the high temperature lubricating oil comes to the cooler. The high temperature of the oil, we want that it should be reduced. If we reduce it in the same water, if we absorb that same heat in this water, this, then the temperature already going to the boiler, the water temperature will be raised by at least 10 degrees, 15 degrees. That much flue gas heat is less required for converting steam. You got the point. The efficiencies are to be improved. They
Yes.
are routed, this condensate of the steam is routed through these heaters only for the purpose of raising the temperature of that before it goes to boiler. You know what is air boiler economizer? What we do in economizer? We are also preheating the feed water going into the boiler so that the heat generated from the fuel will be less utilized. There will be fuel saving. The same principle here.
Yes, sir. Yes, understood.
Okay. Then here, now classification of cogeneration systems. I have discussed the different types of cogeneration just now. So let us see how they have classified. One simple and basic classification, they will ask you whether it is a topping cycle or bottoming cycle. Let us not confuse with the words. Topping cycle means what? What is cogeneration? First we understand. That same source of fuel, heat generated by that fuel is used for two purposes. One is the primary production, second is the process requirement of the heat. Now the question is, which use is earlier? That means heat is generated in boiler, steam is generated, fuel is burned, steam is generated. Where you will use the steam first? if your process requirement is of low pressure, low temperature steam, but the boiler steam has high pressure, high temperature, I will use this steam first for steam turbine generating electricity. First, though the primary aim is process, but because the parameters of the steam generated by the boiler are high pressure, high temperature, I am using the steam for turbine generating electricity, and the turbine exhaust is adjusted at a such pressure and temperature which is the requirement of my factory process. I want a factory process steam for 20 kg per centimeter square and say 250 degrees centigrade. So I will allow the steam to cool down or reduce the pressure in steam turbine till I reach the parameters of 20 kg and 250 degrees centigrade. And then from the turbine I will exhaust it and use for process. So my purpose of heat for the process is achieved. But simultaneously I have generated electricity. So when I first generate power, it is the topping cycle. That means the power on top and heat is at the bottom. Clear? No ambiguity in that because there will always be a MCQ on this. What is topping cycle? What is that? If it is reverse, that means first the factory parameters are met. Some factory processes are such that they need high pressure, high temperature steam, which is generated by boiler. So the boiler output of the steam will first go to factory and the factory process will be tapped at a pressure and temperature required for the steam turbine. That means first factory need will be attended and then the exhaust of that process will go to steam turbine and then they will generate power. So first heat and next is the power generation. This is a bottoming cycle. When power is at the bottom, it is bottoming. When power is at the top, it is the topping cycle. If difficulty, you ask me, what is that? So here, that is what they have shown. See the diagram. It's a combined cycle. No, they have done the heat recovery, steam generator. Here it is a gas compressor, whatever. So first they are generating, see here, high pressure steam entering a turbine, exhaust is taken and low pressure used for the process. First, the power is generated. So this is a topping cycle. See, topping cycle. Now, let us go to, this is also topping cycle, only with the diesel generator. The bottoming cycle, if you look at, here, the fuel is generating heat, but very high temperature heat is required for roasting purposes cement industry. The gypsum solids are to be roasted to a desired value. So the fuel is burned in combustion chamber. The combustion chamber goes to the roasting chamber and the exhaust of this roasting chamber, which is very high, about 700 degrees centigrade, is allowed to go through a filter to a boiler. This boiler will generate power. A turbine is rotated and a generator is connected with this. So in this system, first the process heat is used and the exhaust of process heat is given to the boiler. So this is bottoming because power is down, first is heat. That's the only simple meaning of topping cycle and bottoming cycle. The principles of extracting the heat, required pressure, temperatures, they are same. Okay, what are the, now we have learned what is cogeneration, how it is done, what is the topping and bottoming cycle, right? What are the problems a energy auditor has to face when he goes to industry? If he is going to give them some advice that this process, oh, sorry, key gadbad. Yes. Now I want to minimize this. Yes. So factors which are influencing for the choice of what type of cogeneration you want to choose. That is what a energy auditor has to decide. The selection and operating scheme of a cogeneration system is very much site specific and depends on several factors as described below. That means there is no universal law. You can say, oh, first steam turbine and then process steam, or the first process steam and then steam turbine or gas turbine, nothing. Depends on the situation, parameters, requirements of the factory, the pressure and temperature values varying as per the manufacturing demand. So what else influences? What factors you should consider in deciding the choice of cogeneration? One is base electrical load matching. Now let us understand what is base load. Every factory has a fixed manufacturing schedule. Now the manufacturing schedule volume, suppose take any product. My favorite example is I am manufacturing plastic buckets. Now my small factory produces 10,000 buckets per month. So long as I am maintaining that volume, my electrical load is fixed. My heat requirement is also fixed. Fixed goes on. Monthly bill, suppose 3 lakhs, 4 lakhs, whatever is my electric bill, that is coming steadily. But when I am using this electricity, the process are different. Means when I actually start using injection molding, the electrical load is more. Suppose my molding shop is stopped today or stopped for 4 hours, and other processing units on the plastic buckets, they are going on, they are consuming less electric power. So for 24 hours of the day, my electrical load is not constant. That is the case of all electrical loads. As we have discussed, even the grid load is not constant. To morning peak, it may go to 10,000 megawatt. Afternoon, it may be 9,500. In the midnight, it is hardly 6,000 megawatt. It varies. So your generation also should match what is your demand. Suppose the factory says, sir, my electrical load varies between say 5 megawatt to 4.5 megawatt. Okay, then we will say, if this variation is there, should I give him a electrical plant with 4.5 megawatt capacity or 5 megawatt capacity? Which one? Because electrical load will constantly give him the same load. So part of the time, he may not use 5 megawatt. His requirement is only 4.5. What about the 0.5 megawatt which he has extra? So what the owner says, sir, 5 megawatt investment is more, 4 megawatt investment is less. You give me a 4 megawatt plant, remaining 0.5 whenever I need extra, I will buy it from the electrical grid. I am already on electric connection is there. So whenever my own generation is shortfall, I will take it from the grid. So if you give him a system to match his minimum load, that is called base electrical load matching. Conceptually understand. Thereafter you can read and you will understand. This is one way. Another is, he said, my thermal load matching is to be done. That means my process requirement of heat is so much. In all cases, I am not using less than this thermal load, heat I want. So what I will do, I will give him a plant which will fulfill his minimum thermal load requirement. But then what about when his heat requirement increases? What he will do? Then I will give him a supplementary small boiler with a small capacity which is sufficient to meet his requirements of that difference in the heat load. So partly when that Additional requirement comes, he will fire the boiler and get the heat, or otherwise the boiler will be stopped in cool down condition. This is called the thermal load matching. So I am giving me a cogeneration plant having capacities either fulfilling his minimum requirement of electrical load or minimum requirement of the heat required. These are the steps by which you can develop a cogeneration system at optimum cost, give him a viable solution to that. Then third is the electrical load matching and thermal load matching. What are these two things? Same thing, no? Electrical load matching, base load. Electrical load matching, but the base word is not here. That means what? If my requirement is 5 megawatt occasionally and the base is 4.5, if I give him a plant for 5 megawatt, that means the upper edge of his requirement, electrical load, right? Then the owner says, sir, whatever happens, cost is no problem. You give me my full capacity electrical assurance. In no case, I should be able to take the power from grid. Whatever surplus 0.5 megawatt is there, now government has a scheme that they are buying the power into the grid at certain rate. So whenever I have a surplus power, I will put a import export meter and use it. That can be one solution. The fourth man says, I'm not worried much about electrical because electrical I can always buy and sell. You give me a matching with my thermal load. Don't care about electrical. Thermal load, because heat I cannot buy from the grid. I should have my own source. So give me a large source, large boiler, single, who is adequate to meet all my heat loads all the time. Because I have a chemical plant and I can't afford to stop the heat because my entire chemical solution will go waste. One batch will be wasted and that is costly. In that case, you give him enough heat source, boiler, or say gas turbine or whatever, which is adequate to cover all his thermal requirements, right? Then the question is, what happens when he is not using that heat? If he utilizes, fine. But now he has a surplus heat because the boiler is of that capacity and he is using part heat. Then whatever marginal surplus heat he has, he can lend it to the nearby industry or supply the heated water or the nearby industrial MSMEs. He can offer them at a discounted rate that I will provide your heat requirements for the process you need occasionally and then earn some money out of it. Doesn't matter. But at least his business is insured. So these are four types by which you can match the loads. Either match base loads or match maximum loads. Electrical or thermal, both. Correct so far? Any doubt you can ask me. Then important technical parameters. These parameters mostly asked in examination for definitions. They will ask you what is heat to power ratio, what is energy utilization factor, and you should understand or rather rut karo, padho, and then always write in the same wording as written in the book. What is heat to power ratio? Is one of the most important technical parameters fine influencing the situation. It is defined as the ratio of thermal energy to electricity required by the energy consuming facility. What is it? Again, let us understand. It is defined as the ratio of thermal energy to electricity required by the energy consuming facility. That means what? The factory needs some thermal power and some electrical power. Okay. Now, if the thermal power is on numerator, that means upper side of the line, it is the thermal power and the electrical power at the bottom. It gives you a heat to power ratio. And therefore the units are like this. BTU or British thermal units, we are not using this. We are using kilocalorie and kWh. These are metric units. So the kilocalorie requirement and kWh requirement give you the heat to power ratio. As the word suggests, heat to power. Now, why this heat to power ratio is important to understand? See, basic heat to power ratios of the different cogeneration systems are shown here normally. If you use a cogeneration system of back pressure steam turbine, heat to power ratio is 4. Means what? If you take a complete boundary to boundary project and the heat generated by the fuel is so much, then the thermal load is 4 times more than the electrical load. Then in that case, you use back pressure turbines. Here also, let us look at the units. kWth means thermal and kWe means electrical. So the heat units are converted into electrical units so that the ratio can be same. Ratio cannot be having two different units. So this is kW, this is also kW, their ratios. So depending on what type of heat to power you. Suppose you want a cogeneration requirement of 1 to 1, like a combined cycle. That means same units of electricity kW and same units of thermal nimme, half you want. Then the better recommended method of cogeneration is combined cycle. When there is a difference of 1 to 4, that means the ratio is 4, the back pressure turbine is there. Then it is 2, you can use extraction condensing, both the parallel weightage is given. Gas turbine 1.2. So this will basically, as a thumb rule, will recommend this type of cogeneration system. We have seen cogeneration system, what types of cogeneration system, isn't it? Topping cycle, bottoming cycle, whether it is gas turbine, steam turbine, reciprocating engine, no? These are different types, no? Types of cogeneration. Okay, then let us go further. The cogeneration uses a single process to generate both electricity and usable heat or cooling. The proportions of heat and power needed, that is heat to power ratio, vary from site to site. So the type of plant must be selected carefully and appropriate operating scheme must be established to match the demands. Matching the demands again we have seen base load matching, maximum load matching for thermal as well as electrical. So 4 types. Typical heat to power ratios for certain energy intensive industries. This is also proven. If you go to breweries, the heat to power ratios are around 3. If you go to pharmaceuticals, it is 2. That means 2 is the thermal load, 1 is the electrical load. Here in breweries, 3 is the thermal load and denominator 1 is the electrical load. Fertilizers, again, ada 50-50. Food, 1.2. Paper, 1.9. So you will find here in all cogeneration plants, the requirement of heat is predominant. Electrical is secondary. Even in sugar factories, where there are lakhs of tons of sugar is generated, the electrical load they are generating is only 5 megawatt, 7 megawatt, 6 megawatt. The largest I have seen even is 10 megawatt. And that too, they are allowed to use partly coal as a fuel because their bagasse is not sufficient to generate 10 megawatt power continuously all the year round. So remember, cogeneration plants are not for electrical generation. Primary intention of the cogeneration is to fulfill the heat loads, and surplus heat can be diverted for electrical generation under different methodologies. Okay. Now cogeneration is likely to be most attractive under the following circumstances, where you will recommend cogeneration as an energy auditor. First condition, the demand for both steam and power is balanced. That means you have a heat to power ratio 1. Same, whatever is numerator, whatever same is the denominator. That is ideal. The single plant or group of plants has sufficient demand for steam and power to permit economies of scale. Now, there are different process factories. One is a dyeing mill in the cloth. Another is the paper and pulp mill. Third is some other painting shop or spray shop, whatever. They are in a one cluster of industries. Then the largest producer of heat can distribute the load of heat and power among these different processes. A ideal full efficiency can be obtained from such cogeneration plant. They can have both the electrical advantage as well as the thermal advantage. Peaks and troughs in demand can be managed in case of electricity. Adequate backup supplies can be obtained from the grid. Utility company means from the grid. So these are the ideal or attractive situation where cogeneration will be most beneficial. Once you understand why cogeneration is required, what is the purpose, objective, then you will never make a mistake. You can straight away say where you will recommend cogeneration, where you will not recommend cogeneration. Whenever there is very skew balance, that means the heat load requirement is only 1 and the power requirement is 4. So peak ratio going much below 1. You will say it's not an ideal situation for cogeneration. Cogeneration is where the primary heat load is more and the secondary generation like electrical is less important. Only thing when we say topping cycle and bottoming cycle, depending on what parameter heat source you have. If it is high pressure, high temperature steam, first it will be topping cycle. That means it will generate first power. But while generating also, a small quantity of required electricity generated, bulk heat is given to the process. You get my point, right? If the parameter of heat source is of low pressure, low temperature, then in that case, it goes to the process first and then electrical generation. So topping and bottoming cycles, these are the further variations, but the basic requirements of recommendation, you can decide what is their thermal and electrical loads. Now, energy utilization factor, EUF, is the percentage of useful output, a combination of electrical and thermal together, depend on what is the input. As an auditor, you must always remember what is efficiency, whether it is process efficiency, it is a boiler efficiency, turbine efficiency, anything. Output upon input percentage is efficiency. Now, output in which form? Whatever units you decide, the same unit should be in the denominator. Otherwise, it will not be ratio because efficiency doesn't have any unit. It's a ratio. So output upon input is efficiency. Now, in case of heat, what is that? In cogeneration, output is in two forms. One is electrical, another is thermal. But if this output is to be combined and divided by the input of the fuel heat, the upper units are also should be thermal. That means heat given to the process is already in thermal, that is kilocalories. But the electrical output you will have to convert into heat units. You will have to convert into heat units. Now, what is the unit of conversion? 1 kWh power is equal to 860 kilocalories. I have told you in the morning session. So whatever is the kWh electricity generated multiplied by 860, so much will be the heat equivalent of the energy generated, electrical energy. Plus add the kilocalories you have supplied to the process, you get the output in heat units. In denominator, how will you calculate the input? The number of kgs of fuel, how much kilos of fuel is burned, multiplied what is the gross calorific value per kg. Multiply both. For example, if it is a case of gas, if it is 10 kg of gas, the calorific value of gas is how much? You must remember, they may not give you. You remember it is 10,000 kilocalories per kg. So much kgs of gas burned multiplied by 10,000. So much calories is the total heat input. And what is the output? The electrical equivalent of kilocalories and the kilocalories supplied to the process, add and divide by the total heat input. That will give you the how much percent of energy you have used. That is what the factor says, energy utilization. I give you X amount of heat, how much you have utilized it gainfully. When you take this ratio and you find it is much below, oh, it's only 50% or 55%, then a energy auditor starts back checking where the losses are occurring, why the energy efficiency is low, utilization factor is low. If it is 80% and above, wonderful. Then minor 10%, 20% losses you can account for. But if it is a major chunk, that your utilization factor is hardly 50, that means you are wasting the remaining 50% heat. And where it is wasted, you check the processes, try to improvise. That is the tool in the hand of energy auditor to check the EUF and find out where something is going wrong. Okay. The quality of thermal energy needed. Now, as we say, what is the quality of electricity? How do you judge? It is the frequency and the voltage, two parameters. They will decide whether the electricity of standard is reaching to your place. Frequency is 50 cycles per second. And the voltage you need in the domestic, it is 215 volts. If it is three phase, 440 volts. Standard parameters. If you get this parameter, you say, yes, electricity is of good quality. Similarly, for thermal, what are the parameters? One is the temperature. What temperature you are getting? For example, wood burning. You are burning a wood, you may put a very large amount of wood and create a fire. The maximum heat intensity you can get is limited to 300 degrees, 350 degrees. At the most 500 degrees if you supply the fire conditions are ideal. But if you use petrol, if you use pulverized coal, the temperatures in furnace can go as high as 900 degrees centigrade, 1000 degrees centigrade. It shows the quality of heat which you are getting. Any heat generated into the atmospheric condition, open atmosphere, the atmospheric turbulence will not allow the heat to be intensified. It gets diversified. And so the temperature reached are always less. So let us discuss what is quality of thermal energy you need. Temperature and pressure also determines the type of cogeneration system you want. For a sugar mill needing thermal energy at about 120 degrees centigrade, a topping cycle generation can meet the heat demand. On the other hand, for a cement plant where thermal energy of about 1450 degrees centigrade is required, then the exhaust of that is the bottomic cycle, can generate power. So here the bottomic cycle is acceptable. Here the topping cycle, because whatever is your need, that need, how it can be met, either we met with the fresh steam or the exhausted steam, like that. Process required. Yes, whatever we discussed on the load variation, this is what they have shown. A factory A and factory B. Now factory A, over the time, their electrical requirement is this. No, dark line, this is electrical. That means their load in the morning is less, then it increases because some processes they start in the afternoon and very high consumption of electricity. On the contrary, when the electrical requirement was less, the machinery was down. At the same time, the furnaces were operating full because they wanted heat to be sourced to the process. The processes which are using heat are maximum in the morning time. Afternoon, there are less requirement of it. Whereas in the morning, electrical is requirement less, afternoon it is high. It's a odd picture of using. They are not simultaneously using both energies. Here, in this process, factory B, their heat and electrical energy run in parallel. Same. In the morning, if they are low, both are low. If it is high, both are high. So here, the type of cogeneration which you will be giving should match the load pattern. Got the idea? And then accordingly, the fuels availability, system reliability, you will have to design. So what are the factors which will be governing the quality of thermal energy needed is pressure and temperature, load patterns, fuel availability. In some places, high intensity fuels are available. That means LNG, CNG, good, or the compressed biogas, CBG, good sources of. But some places only coal is available. At very remote places, even coal is difficult to transport. So they will have to go to biomass or wood and all that. So depending on fuel availability, you will have to design it. Here, a rice mill needs mechanical power for milling and heat for paddy drying. If a cogeneration system were considered, the steam turbine system would be the first priority because it can use the rice husk as a fuel which is available in waste product at the mill. So depending on what is easily available, economically available, viably acceptable, that kind of fuel will be used and it varies from site to site. Then the system availability. Energy consuming facilities require very reliable power and or heat. For instance, a pulp and paper industry cannot operate with a prolonged shutdowns. In such instances, the cogeneration should be installed, must be modular, that whenever you require, you start another module and pick up the additional load or stop a module and reduce the electrical load. That kind of reliability. Then grid dependent system versus independent system. This is just a comparison, most logical. You read through it, nothing difficult to understand. Then retrofitting, what is the existing system and you are proposing a new retrofit system. Then in that new retrofit system, there are so many factors playing parts. One, you can always, of course, go for highest efficiency retrofit. But highest efficiency retrofit may require more space for erection. It may require major changes in the existing system. It may require higher capital cost required, right? So the owner may not accept your proposal. You will have to find a golden mean, achieving all these in a viable manner, and then give him a proposal so that the payback period is small as capital investment in the first instance is less or it is spread over a longer time. That kind of thing. Electricity buyback, the technical consideration of cogeneration system must take into account whether the local regulations permit electricity release to buy electricity consumers or not. Now, of course, we are in an era when even your solar panel on the top of your house roof is being bought by the grid. Grid says, okay, you generate extra and give it to us. You will have credit with us. Either we will pay you or we will return the number of units you have given to us. So, cogeneration plants can have surplus power with a provision to sell it to the government grid. So, there is no danger in designing a cogeneration plant having slightly higher capacities than the requirement of the factory, provided the factory owner is ready to invest in the capital cost of a higher capacity plant. Next, load environmental regulations. What is that? The local environment regulations can limit the choice of fuel. Regulation is that in any mega city, in the locality where population is thick, you can't have a coal plant. Even if it is viable and economical and everything, the regulation says no, you can't erect it here because of the environment problems and whatnot. Likewise, there are many restrictions which are choice site-based restriction, you can say, different sites. So depending on where your factory is located, where you want to put a cogeneration plant, all these will have a legal angle. Whether legally you are permitted to execute that cogeneration plant requirements, right? Then prime over for cogeneration. Now, these reasons, no, these 6 reasons which I have seen, they are all the sources. How do you select a cogeneration plant, right? Depending on. So, this selection of a energy auditor for a cogeneration plant, depending on heat to power ratios or the electrical load curves or the requirements of the factory at the time of requirement when they want simultaneously or one after another, right? You should be able to answer either in short note questions or in a long term theoretical question which also may come. You can go through the past examination papers. Okay, now let us understand what are the prime movers for cogeneration. What is prime mover? Is the main source which provides energy. First is the most complicated is the steam turbine. What is steam turbine? Those who have not seen a steam turbine in open condition, when it is open for maintenance, you can see the upper half, lower half, the arrangement of fixed blades, moving blades. So this gives you some idea. You will find if this is a turbine, the blade height is increasing from this point to this point. The last blade is the tallest blade or the highest blade diameter. They are, when rotating, they form a circle. This is the highest diameter and gradually it comes down. There are different walls. You may not remember the names also, doesn't. Only understand the concept how it works. A high pressure, high temperature steam coming through a control wall enters the first stage of the turbine. This admission chamber allows the steam to flow through this path. Steam path it is called. Now this steam path is a series of fan blades or the turbine blades. The blades are fixed and rotating. I will not go into the construction details. It takes longer time to explain. So remember, one is fixed blade, another moving blade. Now if you can see my hands, these blades, one remains steady, another rotates. So the steam entering from this will have a formation depending on the what is the blade profile. Now this blade profile will enter the steam in the next stage at a impingement angle, the angle at which it strikes. And when it strikes, it gives a force to rotate, like we have seen in windmills and the other areas. So such a accumulative churning goes on increasing and from this point to this point. Now naturally, high pressure, high temperature steam when expands, it increases the volume and that increased volume is accommodated by increasing the volume till the last blade. So the high temperature pressure steam entering here, by the time it expands, rotating the blades and reaches here, it achieves a lesser pressure and lesser temperature. Less pressure. If it is say 150 degrees kg per centimeter square, it may go to 50 here. Now, when this comes out of the last blade, it comes in a chamber, and that chamber then drains it to the condenser. The exhausted steam goes to condenser in a condensing turbine. In a non-condensing turbine, it doesn't go to condenser, but that pressure and temperature steam goes to process heating or industry requirements. So steam turbine can be a condensing turbine, can be a non-condensing turbine. Many times, this pressure reaching to the last tail, say 50 kg, but the process requirement is of 100 kg steam. So you will not allow the steam to reach a low point of 50 kg. It is somewhere here at 100 kg because it entered 150, going down, 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 100, again down, down, 50. So at 100, I will tap it. I will put a pipe nozzle, and here only I will allow it to go to process steam. Not at here, but here, because the process requires 100 kg steam. It will go like this. Suppose it requires 125, I will tap it here prior to 150 and 125. I will tap it and give it to. So one turbine can be extracted or tapped at different pressure points and temperature points, so that it has a wide variety of applications. A plant requiring 3 or 4 parameters of a steam, they can have it. Lastly, if the steam volume is much more, that after fulfilling the process requirement, still the steam is surplus, then that steam is allowed to expand till last and then condense into a condenser, thereby increasing the electrical load output. This increases. Right? This we have seen condensing, non-condensing extraction steams like this. Here, the same is explained here. The high pressure steam, this is the entering. This is the exhaust steam. This is high pressure, but it is not allowed to expand till last. In between, it is tapped for process. This is extraction back pressure. This is high pressure. There are number of points it has tapped. This goes to condenser, but prior to that, at this pressure, it is tapped and taken away for the process. That is what I explained to you. So these are different configurations of back pressure turbines. Extraction is allowed. Again, whatever is already explained above. If this is steam generator, boiler is a steam generator, allowing high pressure steam going to steam turbine. Then this turbine is extracted here at some pressure and temperature, goes to the process. This triangle is process, and process exhaust goes to boiler. Here it is exhausted into condenser, and the condenser output, that is a condensate water, it goes through the process to the steam turbine. So it is extraction and condensing both. Seen, we have already discussed this. Now gas turbine, as I explained, this is a compressor stage. First, it compresses the air and forces it into this combustion chamber, which is showing fire in red. This is a combustion chamber. The atmospheric air is compressed, given to the combustion. Then in combustion chamber, fuel is added, and the products of combustion will go through these turbine blades and go to exhaust. Now this exhaust is of very high temperature, and the heat in the exhaust gas is utilized for the steam generation in the, what they say is the steam generating boiler. The steam generated in that boiler is used for operating a steam turbine. So this is a gas turbine arrangement. Now, gas turbine efficiencies. My request is you go through the entire text of this. I am explaining, no doubt, but whatever you understand, it will be confirmed in your mind if you simultaneously read it today itself. After my lecture is over, it will be remaining in your idea. In the daytime also, every day you must dedicate some time specifically for this study. You have to do it only for 1.5 months, not much. So find time out of your busy schedules. I know you have other compulsions, but still when you have decided to pass this exam, yes, you must determine to find some time, go through this simultaneously, and at any time you have got any difficulty, in my next lecture you raise the point, even if the topic is different, I will explain these things to you. So the gas turbine efficiency, net turbine efficiency, reciprocating engine efficiencies, these are the common points. Efficiencies, as I have generalized, is output upon input. For finding out efficiency of any thermal utility, what is the criteria? The output heat, that means useful heat, which is converted into process or some product or something. That is the useful heat upon the input of heat by burning the fuel. And the simple parameter burning the fuel means fuel in kg multiplied by the gross calorific value. That is numerator, denominator below. And the upper is the output heat. Units are same. So since exhaust gas from the gas turbine high, it is possible to recover energy from the hot gas by the recovery steam generator boiler. Now here, what you have to remember in this is only these two figures. The system efficiency of a gas turbine will be as low as 35 to 40%. Remember, there will be a MCQ and they will give you alternative 60%, 70%, 90%, whatever. So you have to choose gas turbine 35 to 40%. Okay. Net turbine efficiency. What is net and what is gross? Above efficiency figures did not include the energy consumed by air compressor, fuel pump, other auxiliaries. Air compressor alone consumes about 50 to 60% of energy generated by the turbine. Hence, net turbine efficiency, which is the actual energy output available, will be less than what has been an integral part of the turbine. So if turbine alone, that means the heat entering turbine and exhausting turbine will give you the output upon input to say 35 to 40%. But this generated, efficiency, since on the shaft, out of this 35% efficiency, if the heat is to the extent of 50% or 60% is utilized for compressor, then what is the useful heat outlet? To that extent, that 5-10% what is going into the compressor of the total efficiency will be the reduced efficiency of the net turbine. They will give you all the input data, only you have to put it in a formula and explain that this is what the efficiency means. Then reciprocating engines, these are also you read through, nothing special about it. Typical cogeneration performance parameters. How do you check the performance of a cogeneration plant? One, take a smaller reciprocating engine. What is the nominal range, electrical range? 10 to 500 kW is the normal reciprocating engines used for this generation of electricity. Electrical generation heat rate. Do you know what is heat rate? The heat units required to generate 1 unit of electricity. Now again I am repeating. 1 unit of electricity is kWh. Right? So kWh you want to generate 1. Ideally, what is the equivalent of 1 kWh? I said 860, 860. But here this fellow says the heat rate, that means per kilocalorie you need to use heat units, kilocalories, 2650 to as large as 6000. Whereas equivalent of electrical unit is only 860. So where ideally, if the transformation efficiency is 100%, you should have 1 electrical unit per 860 kilocalories of heat. But instead of that, your machine is taking 2650 kilocalories to generate 1 kWh. How poor your efficiency is. What is the efficiency? 860 upon 2650, almost 30%. You are operating the machine at 30% of efficiency. So heat rate always gives you how much your machine is consuming heat to generate 1 unit of electricity kWh. So lower the heat rate, most efficient is the machine. If it is heat rate is only 860, it is 100% efficient, right? But as you get the figures larger and larger, the poorer and poorer the efficiency, because this figure is at the bottom, at the top is 860. So for 860 kilocalories output, if you are consuming 6000 kilocalories, so 860 upon 6300, you can just calculate the ratio efficiency. So the efficiencies of electrical conversion are hardly 20 to 32%. That's what this is showing, 860 upon 60. And thermal recovery is 50%. 50% of the heat is lost to the atmosphere, or your process leakages are there. Total, when you get this efficiency and this efficiency, combined efficiency comes to about 74 to 82%. That means there are still losses of 26 to say 18%. Energy auditor's job is to find out the loopholes, find out where the efficiency loss is occurring. If it is a larger reciprocating engines, you have got some better values. Lesser heat rates, better electrical efficiency. Diesel engines is almost comparable. Small gas turbines, not much improvement. Larger gas turbines, no, because the compressor is eating out a lot of energy. Steam turbines, it's very, very poor. 25, 50, 10 to 100 megawatts. Small turbines, 7 to 34% efficiency. These are thumb rules which have been observed at different capacity of the generators and the co-generating plants. This gives you an idea about, just I have shown you how the high pressure industries like cement and fertilizer, they require high power, high heat power. So similarly, these thumb rules will help you in solving the multiple choice questions. You should often should be able to reply which industry, what is the type of industry, okay, then this is the efficiency, that kind of thing. Then relative merits of cogeneration systems. It's a comparative. What is the advantage? What is the disadvantage? You read through this: steam turbine and fuel firing in boiler. High fuel efficiency rating if it is a back pressure turbine. It is, suppose it is steam turbine, it's simple plant, well suited to low quality fuels. What are the disadvantages? More capital investment, low fuel efficiency, high cooling water demand. Gas turbine with waste heat recovery boiler, good efficiency. Combined gas and steam, this is the efficiency. So each type of cogeneration plant, 1, 2, 3, 4, 5, has got their advantages and disadvantages. This is a guide for energy auditor to decide depending on what is the requirement and what is the plant most suitable from this table which he can recommend, and then calculate the budgets. Then steam turbine efficiency. You have seen the efficiencies of turbine and boiler in your earlier lectures. Same paper, paper 2, different chapters. They are more detailed, they have got more solved problems. Here it is just a reference to that, because in cogeneration or in other generating processes, the working of a steam turbine is same. Efficiency calculation is same. Same thing is for the boiler also, whether it is pulverized or it is APC boiler, that kind of. So these chapters are supplementary chapters to our earlier chapter 2 and chapter 8, 1, like fuels and combustion. So how do you monitor the performance of a turbine? Some nomenclatures or definition you must understand. First is cylinder efficiency. What is cylinder? The segment of a turbine starting from the inlet to the exhaust. That one enclosure through which the steam is expanding is called turbine cylinder. There are turbines who have more than one cylinders. That one cylinder dedicated only for high pressure steam, one cylinder for medium pressure steam, third cylinder for low pressure steam. These are three cylinders. They achieve better efficiency because their expansion ratios are good only for that cylinder. So how do we decide the cylinder efficiency? Let us understand theoretically. When the steam expands, isn't it? The steam expands from say pressure 1 to pressure 2. This is a pressure line, right? Actual plotted on the graph. The pressure was here and it started dropping as it expands. Pressure line with a heat constant. Now, when P1 expands like this, it loses the pressure and the behavior is like this. P2, as it's further reduced, there will be P3, there will be P4 parallel lines. But in theory, the heat does not drop in a straight way. Pressure comes down in a straight line. Total heat content in the steam doesn't come that way. Theoretically, it should have expanded like this. But in practice, it expands like this. So it retains certain higher heat than it should have given up. So what they decide, what is the difference between the ideal expansion and the actual expansion? So AB, what is A? H1 minus H2, H1 minus H2. This is the column, that means the vertical axis where the measurements are there. This is the value of H1 here to here. This is the value of H2 here to here. So H1 minus H2, that is this difference between these two, is A. And what is B? H1 minus H2 isometric, isentropic rather, isentropic, not metric. So this value, look at again, if you draw a perpendicular from this will be the value of total heat, this will be actual value, this will be theoretical value. So this gap between this actual and theoretical indicates the efficiency. If both these points match, if the actual expansion is also as the isentropic expansion, the cylinder efficiency will be 100%. But it is not so. A is always small, this to this. Sometimes in bad condition, this expands like this only. That means it is still further less than the ideal condition. So this is the enthalpy, entropy. These concepts are related with the pressure and total heat in the steam. Let us not go much in detail, but know you should be able to draw this graph and show correctly the isentropic expansion and the actual expansion. Rewrite this formula for cylinder efficiency. Then turbine pressure surveys. These are again, there is no graph and thing. You read and understand the issue involved. Then turbine heat rate. Now again, remember always what is heat rate. When we go to the market and find out what is the rate of this particular item or the what you can say, the vegetables or whatever you buy, what it tells, this is rupees per kg. That means 2 units, and they show the interrelationship. Heat rate always shows interrelationship between 2 units. One is electrical unit, another is the heat unit. Electrical unit is at the top and heat unit is at the bottom. So heat rate always means how much heat is required to produce 1 kilowatt of kWh of electricity. Now this kWh of electricity unit you can calculate either limited to the boundaries of turbine. That means how much turbine heat entry, how much turbine heat outlet, and how much the electrical outlet. So the input heat and the electrical output of the turbine, the ratio gives you heat required for the turbine to produce 1 unit of electricity. As you expand the boundary, if you count it from the boiler, more and more heat is required because there are en route, there are losses, and therefore the net heat requirement total to generate 1 unit of electricity is much more. The efficiency is hardly 30%. If you go to turbine only, the losses are limited and you may have a better efficiency. Notes on cogeneration efficiency, where you use this. Cogeneration efficiency being useful heat output by heat input is not necessarily inverse of heat rate. No. In the case of a typical thermal plant, since the useful heat output is to process is not accounted in heat rate calculation. Slight difference is when you audit a generating plant using coal as a fuel. How will you calculate the efficiency? You will say whatever coal is burned, heat is generated, converted into steam, goes to turbine, goes to generator. Turbine, it goes exhausted to the condenser and electrical output. If you take only the two parameters, final electrical output, final input, total coal, the ratio is the efficiency of the entire system. If you use this formula for individual components, efficiencies will be different for each, whichever you are using the heat component. Similarly, suppose you come across that a coal thermal power plant has an overall efficiency, heat generated to output. If you take that efficiency, it may be as low as 35%. Whereas in a cogeneration plant, you take the case of electrical generation only. So much electrical generation is there. What is the heat utilized and what is the ratio? It is misleading because the total heat input in cogeneration doesn't go all to the electricity generation. It goes to the process also. So the process heat going, if you count as a loss, so far as the electrical generation concerned, your calculations go wrong. That is what he is trying to explain. Back pressure steam turbines offer better system efficiencies up to 85% since all the exhaust steam is used in the process. These are points only different, asking you to compare the efficiencies in different type of technologies depending on how the heat flow is there. If the heat flow is direct from heat to electricity, you get a different efficiency value. If the heat flow is partly diverted for some other purposes, you will also have to count the useful heat in the process which you have got for the efficiency calculations. It is there. Therefore, different types of use, different type of efficiency. And in order to avoid this confusion, this book has given you ready-made formulas. If this is the industry, what is the cogeneration efficiencies, what is the heat rate in different industries, what is the thumb rule for getting the efficiency calculations in different types of. So it is a guide so as to avoid any mistakes in this. Now, there are some examples that the parameters are given. Look at this. Turbine heat rate with 6 megawatt output, normal flow in the process. Now, here the total input of heat, how will you calculate? This is the Q quantity, tons per hour of fuel. Always convert it into kgs per hour of fuel because the gross calorific value is always given per kg. If you multiply directly the ton to gross calorific value, your figures will go wrong. You will have to first convert it into kg multiplied by 1000, 34.8 multiplied by 1000 multiplied by gross calorific value. That is the heat input. Sometimes they may not give you gross calorific value, which is here, not given. Instead, what he has given, what is the total heat content per kg of fuel? Is still better, per kg. That means what? This value multiplied by the number of kgs. So much is the heat input to the turbine. Now, this entire heat is not going to be converted into 6 kW, 6 megawatt. It is partly used for this process extraction, partly used for this process extraction, and partly exhausted into the condenser, right? Now, they have made it very simple that what is the heat content in this extraction, what is the quantity, what is the heat per kg. Again, convert this TPH volume multiplied by the per kg value. This is the total heat going to the process. Same thing, extraction. This much tons convert into kg, multiply what is the per kg kilocalories or kilojoules value, and that is the total value going to this. And third heat going to the exhaust. There all things are given. Flows are given in kg or tons. The total heat content per kg is given. And here you can put a small heat balance. This is the heat input. This is the useful output electrical. Now this electrical output you can convert into heat units, or these are three sources where the heat is diverted. All taken together. This is plus, this is minus, this is minus, this is minus. Make an addition. This addition in the numerator, total heat input in the denominator, you will get the efficiency of the entire system. If you want to take the efficiency of a turbine, then you have to take these values, find out the equivalent of electrical, total heat, and divide by the total input. That will give you turbine efficiency. The same, it's a solved question. Again, I will repeat my instructions. You go through this solved example, go through each step, which formula they have used, and then try to solve the same problem on a separate paper by closing the book. If you could solve the problem as he has solved, clear cut with the understanding which denominator, which numerator, which given value is used in the formula, then you will get the understanding. If you can't do it, again open the book, go back, read through, again try to copy. Go on doing this till you get the complete perception of what values to be used here. That is the easiest way to understand any type of problem. Now, what we have so far discussed is the cogeneration. That means only two sources we are using. The main fuel source is the heat source. That heat generated is divided into two streams. One stream is electrical, another is the heat for process. There is also a third stream, sorry. When it is used for third stream, they call it trigeneration. Now, trigenerations are limited applications, but they are there and you must do it. The trigenerations are, one stream is power, the electrical power can be generated. Second is heating. The hot water can be utilized for processes or the domestic heating. And cooling also by using absorption chillers, which utilize the heat for absorbing creating the vacuum and extracting the heat from the water, converting it into a chiller temperatures at sub-zero temperatures many times, and used for a large refrigeration houses or the large refrigeration systems. So part of the heat is diverted for that. So you know the three streams. One is electrical generation, another is the process heat, and third is the process heat for refrigeration purposes. This is called trigeneration. Not very applications for trigeneration, but remember there is also such thing as this thing. Then when you talk of turbine, we always talk of big things. 1 megawatt above, that means the 1000 kilowatts and above capacity. But many times the industry requirement is hardly 50 kilowatt or say 500 kW, not even 1 megawatt. They are called micro turbines or mini turbines. Now, micro and mini turbines are used in a large plant also, where there is a need to reduce the pressure of steam. Normally, if it is a small requirement, we are using the pressure reducing valves. Pressure reducing valves, PRV. Instead of using this, if we use a turbine here, we remove the valve, put the turbine. The steam inlet is here. In pressure reducing valve, this is the inlet, this is the outlet. Here it is the inlet and this is the outlet. The inlet and outlet of a pressure reducing valve, it only changes pressure P1 to P2. And where P1 is higher, P2 is lower. Temperature 1 is higher, temperature 2 is lower. But the total heat contained per kg of steam here and here is same. There is no heat loss. Without heat loss, a pressure reducing valve reduces the steam parameters, pressure and temperature, to a lower value. Now, here there is no heat loss, but by accepting small heat loss, this turbine can convert a generator to rotate, and a small production of say 4 kW, 5 kW can be achieved without any change in the process value. That means you have recovered 3-4 kW from the work done by PRV, which was not generating anything, but by putting a micro turbine, you can do that. That is the only advantage. It is used for small heat loss recovery somewhere in the processes. So smaller turbines are replacing the PRVs which were originally used. Now, pressure reducing valve versus back pressure turbine. A small parameter is given. You can read through. It's a small example. The different parameters are given and they are explained. Boiler and PRV operations. See, the total values are given, formulas are given, fuel consumption with steam, with PRV, how the steam is achieved, right? How much kW they can generate. These are solved examples. Go through these solved examples. And then we come to the questions. As we solve these questions in the morning, let us take one. A cycle which generated first electricity or mechanical power is called, come on, tell me, whether it is topping or bottoming. First
Topping.
Topping, correct. A power plant which uses first a gas turbine followed by steam turbine for power generation is called
It is
combined cycle. No, it's a
combined.
combined cycle. Gas and steam both. That is why it is called combined cycle. Remember, you must have seen the diagram made in the book earlier. For same inlet condition of steam, which of the following will generate the maximum mechanical power? Same inlet condition of the steam. There are four types of turbines here shown. Condensing turbine, back pressure turbine, extraction cum condensing turbine, extraction cum back pressure turbine. Remember, back pressure turbines are always low efficiency. Remember, pakka, back pressure turbine, wherever the back pressure word comes, the electrical efficiency of such machines is less. Highly efficient turbine is the condensing turbine. That means entire steam is used to the last pressure point for generating power. That is condensing turbine. Fourth, the equipment having the highest efficiency in
So,
case
sir,
of,
answer is a condensing turbine here.
yeah, it has to be.
Okay.
You can again go through the condensing, extraction turbine, back pressure turbine, read through. Answer is condensing turbine, because what he is saying will generate the maximum mechanical power. What is mechanical power? Which torque generated, which rotates the generator.
Yeah.
So the entire heat converted into steam is used for power generation. So the maximum extraction of the steam is achieved by the condensing turbine. It is the steam is getting expanded to the last vacuum stage and then condensed. Therefore, the mechanical power, that means the electrical power, same thing. It's not heat, it's the mechanical power that is used is the maximum.
Okay.
Therefore, it is condensing. The equipment having the highest efficiency in case of a cogeneration plant. बताओ भाई.
Electric generators
Yes,
equipment.
highest efficiency. Remember always, boiler is hardly 85%. All electric motors are highly 80-85% again. Turbines has a better efficiency of 91%. But generators can be highly efficient, more than 96%. Because generator does not have any loss points in it. The entire torque generated by the turbine is converted into electrical energy. Okay, so electrical generator is the highest efficiency point. The efficiency of a standalone gas turbine without any heat recovery system will be in the range of, there is no recovery directly. Just I have read you 35 to 5% we have seen, isn't it?
35 to 40%.
That is the gas turbine efficiency. If the gas turbine gas is not used in recovery heat boiler, the turbine alone can work at 35-40% efficiency. Okay, that is in the book. I have stressed on that point. An axial compressor is used in conjunction with of the following. Axial compressor. On which turbine shaft we have seen the compressor? I told you that this is the gas turbine blade, this is the compressor blade, they are on the same shaft, there is a combustion chamber in between. What
Yeah,
is
gas turbine, sir. Gas turbine.
correct? So let us not forget so easily.
Okay, yes.
That is why you should read repeatedly. Because just 5 minutes back I told you and now you are confused.
Yes.
Right? Then the next is a cogeneration system is also known as
Generation system is also known as
cogeneration means
combined heat and
generation
power.
of, yeah, that is it. When generation of both things, heat and power system combined. So C it is combined heat and power. What is 8? Power is generated from the waste heat of a sponge iron plant. This type of cogeneration is called, now tell me which type of cycle. First sponge iron plant and then electricity.
Bottoming cycle.
Bottoming cycle, yes. When electricity comes after, it is bottoming. If it comes first, it is the topping. Now, air compressor alone consumes about so much of energy generated in gas turbine. C,
Uh,
40 to 50%. We have seen that.
yes, 40 to 50%.
Yeah. Then 10 is a paper plant needs steam at T3 bar. That means 3 kg per centimeter square and 10 bar in addition to electrical power. That means it should have two tapping points at 3 kg pressure and 10 kg pressure. Huh? The most suitable cogeneration choice among the following will be C, extraction come back pressure. The
Yes.
different type of steam is tapped from the turbine. The turbine shaft is used for electrical power, but the steam is not allowed to condense into condenser. In between, it is tapped at two different points. So go back to the picture of the extraction cum back pressure turbine and you will realize that two tappings can be taken, right? So it is the C, that is the extraction cum back. Here you have to only match the figures on page 197. Same table is given in your book. Match the following: cogeneration system and what is the typical range of heat to power ratio. You can go to the book and match them. Draw a sketch of an extracting condensing turbine cogeneration system. Same we discussed. You go and find out the figure. Show some two tapping points, extraction point 1, extraction point 2, steam going to the process, and the shaft is ending into a generator generating some power. What is the heat to power ratio? Again, I said no, you read the definition. Sketch the schematic of back pressure turbine, extraction turbines. Only figures you have to draw. If you could draw the figures correctly, there is no problem. And this big question, the long answer question, has got so much data as always given. So many inputs. Operational data is here. Compare the cost of power generation from a gas turbine installed at 10 tons per hour waste heat recovery boiler vis-a-vis a grid supply. Grid supply cost is given. Calculate your generation cost by putting the heat input, heat to power ratio, and then you will come to the conclusion. What is the cost of that? If it is more, it's costly. If it is less, then cheaper. Steam inlet condition, back pressure, steam outlet condition, back pressure, different parameters. Once you know what is pressure, temperature, and the total heat in a particular volume of steam, you can compare the heat loads and do the calculations. Use the same formula. First, read the solved question papers, solve problem, try to solve the same problem with the same parameters, same figures independently. So long as you are successful in doing that, then you can try new question. So with this, it's already 4 o'clock. So we will conclude here, right? How many? Today there are only 3 students available, isn't it? I think we should increase our attendance here. Where is the diagram? Yeah, it is here. So one new addition, Rathod and Ambadkar. So only 2 were present. Satyanarayan has left already. Hello.
Yes, sir. Yes, sir.
He has left. So only 2 of you there. Okay, then you wait for next lecture.
Yes, sir.
I will have to stop the recording.
Yes.